Hello and greetings everyone. I'll be talking about the liposome and the wonders it can offer in the cosmetic industry. Okay, what are liposomes? Liposomes are nano-sized vesicles that have phospholipid bilayer that surrounds the aqueous core. It has a hydrophobic domain to trap the insoluble agents. While the size of the liposomes is very small, it is about 20 nanometers in size, and it has diverse capabilities and abilities. One of it is low toxicity. The second, it has biodegradability and biocompatibility. Other than that, it is also antioxidant and also has a freeze drying properties. This is very useful, especially in the facial and the skin product that we see in the store nowadays. Though, due to all the abilities and capabilities that liposome can offer, it has a great potential in the cosmetic industry.
Liposomes can be prepared using a wide range of methods that involve a combination of lipids with aqueous media and somehow affect liposomes' characteristics such as size, lamellarity, and encapsulation efficiency. The recently reported methods can be categorized as conventional, which mostly involve approaches that are easy to use at a laboratory scale. The first preparation method is film hydration. Also known as the Bangham method, film hydration represents the simplest and oldest method used in liposome technology. Lipids are firstly dissolved in a suitable organic solvent and dried down to yield a thin film at the bottom of the flask. The obtained lipid is hydrated using an appropriate aqueous medium to produce liposomal dispersion. The structural organization of the formed vesicles can be affected by the hydration conditions. Gentle hydration of the lipid film forms giant unilamellar vesicles, whereas harsh hydration gives rise to multilamellar vesicles with poor size homogeneity, which requires an additional downsizing step. The most commonly used sizing methods include probe and bath sonication that afford the production of small unilamellar vesicles. Although the two sonication methods produce liposomes with identical characteristics, the use of bath sonication remains a better option due to easy control of operational parameters. The next preparation method is the reverse phase evaporation. As the diagram shown, the reverse phase evaporation is an alternative method to film hydration that involves the formation of water in oil emulsion between the aqueous phase containing hydrophilic materials and the organic phase containing lipids and any hydrophobic materials. A brief sonication of this mixture is required for system homogenization. The removal of the organic phase under reduced pressure yields a milky gel that turns subsequently into liposomal suspension. The liposomes can be isolated from the dispersion using centrifugation or dialysis. The third preparation method is solvent injection. This preparation method involves the quick injection of the lipid solution in ethanol or diethyl ether into an aqueous medium. The experiment is performed either in the room or at a higher temperature, for example, 60 degrees Celsius, depending on whether the organic solvent is water miscible or not. The liposomes prepared by the solvent injection process are mostly polydispersed and highly contaminated by organic solvents, especially ethanol due to the formation of azeotrope mixture with water. Solvent injection suffers from several drawbacks, including continuous exposure of the therapeutic agents to high temperature and organic solvent that might affect both the stability and safety of the liposomal products.
Advantages of liposomes as nanotechnology in cosmetic field. Liposomes or spherical vesicles composed of phospholipids that contain aqueous core. It works as a delivery agent that transports active ingredients across the stratum corneum to the deep layer of epidermis where they are absorbed and needed most. Next, liposomes also improve the stability of active ingredients, increase skin hydration by surface adhesiveness, enhance the dermal bioavailability and skin targeting. It also protects skin cells for external stressors such as sun or sweat. Disadvantages of liposomes. As one of the best nanotechnology in cosmetic field, liposomes are difficult to manufacture. It needs high pressure homogenization technique reside in the use of drastic conditions such as high shear forces, elevated pressure and temperature, submitting active molecules to strong mechanical or chemical stresses.
Now I'm going to discuss about manufacturing issues revolving around liposome. Many cosmetic brands such as Lancome, Christian Dior, or Shiseido are transitioning into nanotechnologies by investing to engineer nanomaterials for makeup products and alternative formulations rather than extracting materials from animals, which now is a great concern of ethical issues. However, the mass transition in cosmetic production also means a high usage of homogenizer to produce liposomes for cosmetic purposes in our case, or diagnostic and pharmaceutical applications because of its high shear forces, elevated pressure and temperature. This will submit active molecules to strong mechanical or chemical stress. In addition, particles coalescence can occur because the high kinetic energy and this endangers heterogeneous vesicle. Another issue of liposome production is with the bulk thin film hydration (TFH), which is one of the techniques used to mass produce liposomes. It is a long and discontinuous fabrication time that will require lipid vesicles of not controllable dimensions to undergo further sizing process to achieve nanometric particles. Another method is by ethanol injection (EI). EI is a discontinuous bulk method despite being distinguished by a faster process, which does not allow for control over the dimensional characteristics of the particles, whose output volumes are further reduced and related to those of the syringes used. Hence, there are many researchers to efficiently generate mass liposomes production. Taking two research papers, I will highlight their research findings. From Pamunawa, the skin deposition capability of curcumin-loaded liposome was tested. The FH method, followed by sonic sizing, was used. A similar study by Chen investigated the in vitro skin permeation and in vivo antineoplastic effect of curcumin by using liposome as transdermal drug delivery systems. The traditional TFH method, followed by sonication, was exploited by generating only 1 milliliter of liposomal suspension. To address many limitations characterizing the techniques available for the manufacture of nanoliposomes, a new similar microfluidic technology has been tested for the development of antioxidant-loaded nanoliposomes in additional post-processing.
As a conclusion, liposomes are used as a delivery system carrying active ingredients present in cosmetic products to the deeper layers of epidermis in cosmetic formulations. Liposomes also provide a great source of skin ingredients such as essential unsaturated fatty acids like linolenic acid. From way back their discovery, liposomes have been the subject to extensive evolution in terms of composition, manufacturing, and usage, which led to several openings in both basic and applied life science. An important future breakthrough could be the discovery of cost-effective materials to formulate liposome vesicles with remarkable versatility, with being suitable as vehicles for various molecules while holding a clear molecular architecture to act as cell models for in vitro bioassays. These many advantages far outweigh the disadvantages, and it would be such a waste to not invest more on liposomes in coming times. With that, we end our presentation here. Thank you.